Yeah, thank you all for coming. I see there is a large attendance. I'll try to make it as interesting as possible and hopefully keep you captivated. So, wait, can you see my cursor here? No, well, that's unfortunate. But, well, we can make do. So I'll talk about specializing small language models with less data. And that's the main idea for today. I think I'll try to motivate why would you want to use small language models first. You know, the benefits are local deployment, and they're also just fast and cheap and, you know, all the good things that you want from a machine learning model. But then I understand that training those models is just a pain. You need to label data, prepare it, funnel it to the right pipelines. It's kind of a little bit tedious. So I'll try to give you a brief overview of how we do it, how we specialize models with very little data. So this talk is not going to be a sales pitch. I'll just go through our technical solution and treat it more as a science talk rather than a kind of introduction to our platform talk. But at the end, if we have enough time, maybe I'll show you how our website looks like and so on and so forth. Because obviously we have an agenda here as well. And so yeah, without further ado, let me get started on motivating SLMs. The idea is that many industries like cybersecurity, legal tech, health tech, or any kind of AI fields that require processing sensitive data or work in regulated industries, those companies all operate in a space where cloud access is limited and compute is scarce. Right? So if you want to deploy an AI-enabled feature and run it on your customer's device because of data privacy, you cannot do it with LLMs, right? They're just too large. You need about 1 to 200 grand worth of GPUs in order to run a decently sized LLM, right? So if you want to deploy it locally, on-premise, or even directly on device, they're just not gonna go well. So you need to run small language models, right? So those kind of applications that require local deployment, they need small expert agents. And you cannot just do it with a prompt to GPT-4. So of course you can start building your solution with GPT-4 and alike, but then when you actually want to deploy it in production, you need something much more efficient. And of course I can also say that deploying your solution on top of small language models makes it really fast, really responsive, really cheap. You know, I think that goes without saying. But perhaps it's the ability to deploy it locally that really unlocks a new way of working. So how does that look like, you know, in practice? What would people want to build with those LLMs or SLMs, just to get us all on the same page? So agents are ultimately the way to leverage the ability of LLMs to understand and act on prompts. So in essence, you know, an agent is an LLM or any language model with a very specific prompt. And the prompt tells the LLM to break down the process of answering complex questions into, you can use the prompt to tell the LLM to break down the process of answering complex questions into a sequence of steps. So ultimately, you kind of have a single agent with one prompt that completes one task, but you can chain them together. You can chain agents together in order to solve much more complicated problems than a single agent could kind of do. And I'm sure I'm not the first person to tell you about agents. It's kind of everywhere recently. But the idea is that if you have this notion of a multi-agent system, as in a system that is composed of smaller individual agents that together can work on a very complex problem, the second question that kind of comes in is efficiency. So if you chain 10 LLM prompts, you know, you're really running into the problems that I've just discussed. You cannot deploy it anywhere. The latency is off the charts. Even the cost can be high. So that's why we strongly believe that as AI applications mature, there's going to be this shift towards efficiency in terms of local deployment or lower latency. And it's going to be especially visible for those multi-agent systems where you chain many kind of language model calls together. And the idea is that SLMs are perfect for expert agents because they are accurate. So once you fine-tune them to become an individual agent, right? So if you fine-tune a small language model to solve one narrow problem, they can become very accurate, even more accurate than prompted LLMs. They are efficient because they're small, they're just really fast, so latency is not a problem. And they are secure because I said they can be deployed on-premise and therefore no sensitive data leaks out to the LLM providers. The idea is that you can then use those SLMs to build your AI applications in a very kind of very good way. So, what are types of expert agents that you can work through? Right, so there are quite a few tasks like classification, information extraction, question answering, or function calling. And in general, I just want to talk about a little bit a few practical applications so you can maybe put this theory to kind of more real-world examples. So, for example, for classification, you can triage and route requests into most appropriate workflows for AI assistants. So for information extraction, you can, take unstructured text like a transcript or, some documentation and automatically extract important fields. You can also treat information extraction. You can also use information extraction to treat PII redaction problems. So that's what we're going to work through today in just a second. For example, you have unstructured text with names, phone numbers, etc. You can essentially extract all the sensitive tokens so that you can redact them and replace them with something that is safe. For question answering, those can be, answer customer questions about the system that they're using, provide answers about access to specific documentation, so on and so forth. I guess the general theme is that those agents can do it all, but can then only do one thing at a time. So if you think about an expert agent, you have to have a description like one of those that kind of narrows down the scope, and then you're probably more or less set to train an agent for that task. And I can imagine that if you're working with models, with LLMs, you have run into problems like this in your kind of daily lives pretty frequently. So the idea is that every one of those prompts, or like task descriptions, can be turned into a single expert agent. And then, you can train an SLM to solve it. So this is all fun and games, but, expert agents are difficult to build. Like, they're not trivial to build. So there are two main problems. There is the data. Like, you actually, in order to train anything in machine learning, you need data. It all sounds fun, let's just do AI, but actually you just need labeled examples, and that's kind of really difficult. Data wrangling is notoriously 80% of any ML project, and this is all the same here. So if you want to train an agent like this yourself, you think, okay, look, I want to deploy a small model. It's going to be fast, it's going to be efficient, it's going to be amazing. But then you're maybe possibly hitting a wall of, oh, I actually need 10,000 labeled examples, and I really don't want to sit here and label 10,000 examples by hand because that sounds like hell. So, it can be an issue. The second time is just, it takes time. So obviously there are solutions to the data problem, and I'll talk to you about one of them, one of those that we like. But they all require a lot of time. You can hire external annotators, of course. You can try to build your own pipelines for synthetic data, and label the data yourself. One way or another, it takes weeks, if not months, to get it done. But even once you have the data, you still need to chain together quite a few tools to train and deploy your model in production. And I'm sure all of you are capable of doing that. So the skills part is maybe, I should have removed it from the presentation. But nevertheless, it's not going to take a day, right? Maybe there are some things that you need to brush up on. Maybe everything that there is to know you already know. But one way or another, you will still need to go through the legwork of actually setting up the training and then deployment pipelines. And time is always of the essence. Like, at every job that I've been in, we're always 2 months behind with our development roadmap, and I can imagine that the same goes through for every other company. So you very rarely have the time to take a month or two to set up a training pipeline in order to deploy a local agent. So that's kind of the biggest concern, is that it sounds fun, but actually no one has the time to do it. So our solution to this is essentially to use model distillation. So, for the time, I guess the solution is to just use a managed service like ours, but for the data part and for how do we actually get it done, the solution is model distillation. So the idea is that you can start with very few inputs, which is the task description. So your prompt to what you're actually trying to build, right? We've talked about this, about redact PI information from the text, classify customer service requests into one of the categories. Those are kind of examples of task descriptions. And we're also using a very small seed data set. So that's, just to put it in perspective, that's 10 examples. That's not 10,000 examples that you normally need for training. That's 10 examples, right? And then additional data, which is documentation about the problem. It's just very helpful to have any unstructured data that you can find. It's just very helpful for in any low data regime. Any additional signal is just helpful. And given those inputs, we synthesize new examples using a large language teacher model. So given your job description, the few seed examples and the unstructured data, we synthesize new examples and then validate generated examples to make sure that they are actually of high quality. And once we go through that loop over and over again, we acquire a large labeled data set. And this data set is then used to fine-tune a small language model for it to become an expert at a given task. And then the model is given to you as the user. So that's kind of the high-level idea. And I understand this is maybe a little bit abstract. So what I want to do is to essentially go through one use case of information extraction. So here we'll do a PI reduction case. And I'll try to walk you through how every step of the way works. So if you want, you can just kind of set it up yourself after the talk. I mean, hopefully. We'll see how far I get in 10 minutes, but hopefully it will be relatively straightforward. So, PI reduction use case. So the goal is to produce a redacted version of customer support or text that removes sensitive personal data while preserving operational signal. So we essentially, the input is, a text from our customer. So let's say, please verify account with something, and send an update to an email. And then we redact the sensitive information and then store tokens that are those sensitive examples. So that's a pretty straightforward, expert agent, very clear task. It makes sense. You don't want to use a GPT-4 type model for it because it's actually relatively straightforward, but it's too hard to do a regex matching thing. And it's beneficial to deploy this locally, right? If you want to redact sensitive information, you probably don't want to send it to a third-party provider to do it because that kind of ruins the whole point. You want to do it locally before you send it anywhere. So it makes sense to have something running locally on device. Maybe if you have a broad browser app, you can actually deploy the smallest models in browser, right? They're like 100 megabytes worth of model. So how do we actually do it in practice? So we can use an LLM to cheaply generate new data. So in this example, what we do is we prompt the model saying, generate new examples for the customer support text that should follow a structure of blah, blah, blah. There is a limit of how much text I want to include in the slides, but you get the gist of it. And you can also add a notion of base your generated text on one of the seed examples. If you have 10 examples, that's very helpful. So you first generate new inputs, so new customer support texts, right? And let's say the result is an example like this. So you prompt your favorite LLM with this prompt, and what you get is essentially, please verify the account and send the update to Alex. So in the second step, you use an LLM as well to solve this problem, right? So you ask it to produce a redacted version of the input, and then you give it the text. So the input is then what we had before, and the output is the redacted text. So I kind of simplified it a little bit here. We also had those extracted tokens. I've simplified it here so that you get the idea. But I think it's rather straightforward. So you ask the LLM to generate new inputs, new synthetic inputs, and then you ask the LLM to solve those problems. And then that's how you get a training data, right? You can do it over and over again, and we'll see. So then once we have a batch of examples, you know, let's say we've run this kind of problem, we've run this prompt, let's say 200 times, we got 200 examples out of it. We cannot just start training straight away. So what we do is we want to remove certain types of problems. So for example, if we have two examples that are the same, so you can imagine if we prompt this model with this task twice, it can just generate the same thing, right? So we essentially want to remove any duplicates that we have found. And of course, you know, duplicates mean exact match, but also there is some sort of similarity notion that you can employ. And the better your measure for similarity, the better this works, right? So if you can really find out if two examples are similar, then you can remove similar examples, and then you have a diverse data set. That's kind of the idea. Second part, you just remove garbage, obviously. You know, you can have some heuristics. You can have another agent, if you will, to kind of flag bad inputs, because obviously you don't want to use that in training. So we remove incorrect examples. And in this case, we want to also remove data in the wrong structure, right? So if you have an input of please verify Alex at x.io, the LLM can output your answer essentially in a clear text, right? For example, reacted shared text should read blah, blah, blah. The entities are blah, blah, blah. And we don't want that because we like our JSON outputs. We want this to be consistent with our ideas. So we remove data in the wrong structure. All right, so that's kind of what we did, more or less. Like there's a little bit more detail, perhaps, but on a high level, that's exactly what we did to train a model for the PI reduction. Prompt the LLM to generate synthetic data, validate generated data, run this loop up until we've generated tens of thousands of examples, and then fine-tune the model, fine-tune a small language model on this data. So those are the results that we got for this exercise. So here we compare the teacher model, which is essentially in this case it was Llama 3 70B. So that's like our kind of LLM. It's not the largest, but for the sake of this exercise, it was okay. Then the trained student, which is a small model that was Llama 3B, trained on our synthetic loop. The seed student, which was essentially a student model trained on, it was the same Llama 3B trained on just the 10 synthetic examples. And the base student, which was Llama 3B prompted with our task description. That's how far prompted with the task description and example. So red bar is how far you can get with prompt tuning effectively. So that kind of shows you maybe one thing is that prompt tuning doesn't actually get you that far. You can write elaborate prompts, but there is a limit of what those models can do without actually updating the weights. If you just train them on 10 examples, it's a surprisingly big lift. That's interesting to note. But what you actually, you know, getting the last percentage points is what's really important. So if you then use the teacher model to train it further, you really become close. So here it's kind of, you know, it's more or less 2 standard deviation apart. So, you know, if you run this quite a few times, sometimes you get the student that is better than the teacher. Sometimes it's worse. Like on average, it's a little bit worse, but it's really within one standard deviation. So you can really get a decrease of model size by 30x and effectively get the same performance. And Llama 3B is something that you can run on your laptop. You have a powerful laptop. But, you know, let's say you can also train Llama 1 billion, and it shouldn't be very, very, very far off. And that's something that you definitely can run on any laptop. So one final thing, you know, this was just one example. But what I wanted to show you is that this works across quite a few problems. So we have this benchmarking set where we have a very different data sets. I'll show you where exactly are the details of those data sets if you want to follow that. So don't worry about it. I didn't make it up. But the idea is that we essentially run the same evaluation test of trained student, teacher, seed trained student, and the base student, so untrained model, on quite a few data sets. And as you can see, in general, either the difference is minimal, so it's the same idea, one standard deviation apart, or in some cases like e-commerce, track, or mental health, the trained student actually outperforms the teacher model. I think on average, the trained student models are just as good or better than the large LLMs, but then they're 30 to 50 times smaller, which means you really get the benefit of efficiency and local deployment. So that's kind of the idea. And then in the last 5 minutes, let me show you how we can do that. Mirror screen, very good. So, well, that doesn't work. That's unfortunate. Maybe I can just do it here. This will be a bit scuffed because I cannot see my mouse. But yeah, the idea is that this is our blog post. I'll give you a link to this in a second. So from here you can essentially you'll be able to read everything that I just discussed. In a written form. But here you can go into our website. You can play with this nice animation. But what you can also do is sign into our app, right? And then you can see all of your models and create new ones. What we can do is actually, let's say, create a new model. I'll call it QA test. We'll create a question answering model for our case. So we select that our task is question answering. It is contextual because that's kind of like the standard RAG setup, right? You have the context, you have the question, you answer the question based on the context. That's kind of the idea. We don't have unstructured data, let's say, so we need to synthesize everything. So we go ahead and go into the job description. We can download an example that we can then, okay, let's say, let's use this one because I already had it here. Oh no, this is the wrong one. Wait, this is not going to work for this. I need to, oh no, downloads. Yep, here we are. We upload the job description, so our task, and the description of the context, because we said that we don't have any of them. Yeah, we continue to do the training data. What we do is we can upload our examples. So here are just the templates, right? Obviously, you can upload your own data. That's going to be probably more useful than if you use the templates. Those are just 5 question answering examples. The same for test data, and this is all described like how the data should look like. And what you need is 5 examples. That's kind of the idea. Then you continue to teacher evaluation. The teacher evaluation checks if the large language model can solve your problem, right? So if your problem is solvable. So we don't want you to train a model that essentially says, look, guess what number I'm thinking about. This is just not going to work. So that's kind of an easy way. It takes a few minutes only to kind of check. I'm out of time, so I will not wait for this. I'll show you a model that I've trained before. Teacher evaluation. Yeah, so if we've trained a model like this before. So for the teacher evaluation, you can see that we have a bunch of metrics, and you can see how the teacher solves the problem. LMS judge 93, that's like kind of good enough. So then we can go on to the training, and once the model is trained, you can see the results. It's again the same metrics, and you can see that in this case it was question answering about Roman Empire. The trained student actually outperforms the teacher, and in this example, the teacher is 50 times larger than the student model. So that's a pretty good that's a pretty good result, and you can get it all done, within one session relatively quickly. Yeah, this is our teacher evaluation from the previous model. You can get it once you are happy with the results. You can start the SLM distillation, and we will take it from there. So yeah, that is it. I really invite you to try it out. And what I will also want to show you, oh yeah, this is the QR code for our blog post. From the blog post, you'll see our site. You can go to our platform. You can read about what I've just told you in more detail. There are all the data sets that we have used are there. All the tables with the results are there. I think it's going to be helpful if you want to revisit any content. You can just go into that blog post and see. Second thing is we have a table right over there. You know, just go that way next to the windows. So if you have any questions, if you want to train small language models, or if you have any questions about training small language models, or any questions about data efficient training, you know, anything you like, honestly, we're happy to talk, right? Anything you want to talk about, we're happy to talk. So just come and join us. And that's it. 3 ways. Read about this on the blog post, go into the platform, train the model yourself, or come and join us and talk about it. Those are your options.
Thank you very much, Jacek. Thank you very much for this insightful presentation. And we have a lot of questions, so, so be prepared. The one that was the highest voted is, how would you ensure enough variety when generating new examples with LLM if there is only a small number of seed examples? Couldn't this introduce a bias from the LLM and collapse in production under real users?
Yeah, that's a great question. So I think that's all of this business with validating the data that we generate, right? So there are two main ways that we ensure, 2.5 main ways that we ensure diverse data. So the most obvious one is removing duplicates and removing similar examples, right? And I think that's kind of what I mentioned about similarity metrics. So of course, if you have binary similarity, you can remove examples that are the same. That's obviously a good step, but it doesn't get you all the way there. So the idea would be to embed your examples in some sort of semantic space and then compute the similarity, and then remove similar examples based on your similarity threshold. So you're going to be as strict as you want in removing similar examples. So obviously, that kind of means that your generation process can take a little bit longer if you're removing a lot of similar examples. So you just need to generate a lot more so that you're left with enough after pruning. But that's kind of the main way to remove similar examples. The second part is the unlabeled data. So as I mentioned here, base on generated text, what we prompt the LLM with is base on generated text on the following examples, which is we provide the seed examples. But if you provide any unlabeled documentation, that we can also use it to prompt the model to generate examples inspired by some piece of text. So in this case, we can, for example, have random chat logs of users, or even documentation about your field. Like if it's a medical field, let's say, PA reduction in the medical field, we can have random SOPs about operating in a medical field. Right? So if you have standard operating procedures, then every standard operating procedure should map to a few types of conversations that you can have about that problem. And that means that every time we sample a new standard operating procedure document, that will lead to generating different chats. I hope that it makes it more confusing. Essentially, the idea is that if we sample unlabeled data, this will inspire the model to generate different types of examples. And if we have a lot of unlabeled data, we don't necessarily need to use it for training, but we just use it to guide the generation in different kind of rabbit holes, so that we have a large broad spectrum. And finally, that's something that's an experimental feature still. It's about mutating prompts. So every time we ask the model to generate a new example, we randomly sample a mutation to say, let's say, make the example short, make the example long, make it factual, make it open-ended, you know, those kind of things, so that every new generation is actually different. So it's not just the same prompt over and over again.
So that would make up for the variety of
exactly. Yeah, so there are two ways. Mm-hmm. We generate more varied data by grounding it in unlabeled information and mutating prompts, and we remove duplicates and similar examples by validation. So I didn't want to go into all of it during the talk because we only have like 20 minutes, but there's a lot more kind of the devil is in the details, you know?
Yes, and with that we are unfortunately out of time, and we have a lot more questions, so I encourage everyone to go and ask Jacek in person. Thank you very much again for the great talk.